Good morning, everyone. Today we will spend time in chapter 2 of the handouts. And as you can see, the topic is mathematical reviews. So in this chapter, I just have a brief review of the mathematical backgrounds we will use later. Okay, so the aim of this chapter is just to, as I said, just give you a brief review. So if you find that you don't understand this, or there are a lot that you don't know, then you have to study by yourself. Okay, because I think now, okay. First of all, I think we start with the math, and most of the materials can be found in our textbook, showing that. So we start with the method of proof and notation, and this is important because you'll see in our handouts, there are many times, there are many occasions, we will make statements formally. Okay, we will make formal statements using mathematical language, right? And this is involves the notation and the logics, and also the method of proof, because there are many results in which we will go into the details in the proof. Okay, and this is something otherwise, there are some exercises in which you have to prove the results. Okay, so you need this as well. And so there are a few types of mathematical statements. Okay, and first of all, the first type is the conditional statement. Okay. So for the conditional statement, okay, we use, this is the notation we use. We use the right arrow, okay, where A and B, okay, if we have two statements, A and B are statements, right? When we write A implies A right arrow B, we read A implies B, or if A, then B. Okay, so that means when the statement A holds, then we can guarantee that statement B will hold as well, as a consequence of the statement A holding. Okay, so if in this case, then we say if A, then B, or we say A is sufficient for B. A is a sufficient condition for B. And from the logic, okay, A is a sufficient condition for B means to guarantee that B happens, then we need A to happen. Okay, if A happen, then we can guarantee that B will happen. And in the logic, right? Everyone know this. A implies B is logically equivalent to not B implies not A, right? Because they in both cases have the same truth table. So A implies B is equivalent to not B implies not A. So when you read not B implies not A, you see that if B doesn't happen, or if B doesn't hold, then A doesn't hold either. So this is what we can guarantee from this type of statement. And this is why for A to happen, then B needs to happen first. And this is why we say B is a necessary condition for A. Okay, from this sense, from the contraposition statement of A implies B. So to prove A implies B, we have a few methods. The first one is the direct method. Direct method, so we prove from statement A implies B. Okay, so we assume that A is true, or we suppose, okay, that A holds. Then we try to deduce consequences of our assumption, okay, and then to show that B is true or B holds. Statement B holds, right? And this is what is quite straightforward, that this is direct method. But sometimes you will find that direct method is not easy to use for some cases, right? Then we have another choice. We have, which is what we call we prove by contraposition. So we prove by contraposition. Then because we know that A implies B is equivalent to not B implies not A. So we prove, if we can prove that not B implies not A, then that means A implies B, right? By the equivalence of the two statements. Then, and this is what, and this method is called proof by contraposition, because B implies not A, not B implies not A is a contraposition of A implies B. And there is another one, the last one that I will mention here is we use what we call contradiction. The contradiction is not the same as contraposition, right? In proof by contradiction, okay, we know that A implies B is also equivalent to the negation of A and not B. Okay, so from this, then we assume that A is okay, A is true, and at the same time, by contradiction, we also assume that not B is also true. So we apply. Now we make assumptions on the two statements, right? On A and not B. Okay, and then we try to deduce consequences of A, and we try to deduce the consequences of not B separately, and then from the and then to show contradiction. Okay, so if we can show a contradiction, okay, then in doing this, if we are able to show a contradiction, then that means by the principle of contradiction, then A implies B. I think we will. There is one proof in our lesson that we will use the proof by contradiction. To give you an example, okay, of the proof by contradiction, then we prove that if n+1 pigeonholes, sorry, n+1 pigeons, right? The pigeons is a kind of bird. Okay, if n+1 pigeons are placed in n holes, then some hole, okay, at least one hole must contain at least two pigeons, right? Okay, this is simple statement. This is a simple statement. But then to prove this, then we will prove this by using contradiction. Then we let A be the statement n+1 pigeons are placed in n holes. Okay, and then we okay, and then okay, then we let B denote the other statement, which is some holes contains at least two pigeons, right? So here we prove by the contradiction, so we assume that not B holds. So the negative statement of B is what? Is that every hole, right? Every hole contains at most one pigeon. Right? Then if every hole contains at most one pigeon, that means because there are n holes. There are n holes from statement A. From statement A, we know that there are n holes, right? Then, if there are n holes, then there must be at most 10 pigeons from statement minus B, right? So sorry, from statement not B, right? So it shows the contradiction because I think we start with the not B. The not B holes means every hole must contain one pigeon. So now we will try to use the blackboard. So I think that means we have to, from assumption A, we deduce some consequence. There are two parts. And the other part is we assume that B holds. We assume A holds. Okay, and then B not B holds. And then from this, we try to deduce consequences, right? And then if reach a contradiction between the two sides at some point. And once we reach a contradiction, okay, from using the statement from both sides, then we will include by the principle of contradiction that A implies B. Now there is this is okay. Then in the slide, you will see the exercise. In our exercise, in our handouts, I will add from time to time exercise. So that means you can try to do that. Okay, it can be you can treat it as a problem in which you can try to solve. This is in this exercise by using contradiction. We prove that square root 2 is an irrational number. So what is irrational number? Irrational number means a rational number is a quotient of two integers, right? So if you cannot write a number as a quotient of two integers, then that means it's not rational. Therefore, it's an irrational number, right? So if we have a rational number is equal to m minus, okay? So a rational number is m minus n, right? Where m and n are positive integer, right? If we cannot express a number in this form, then it's irrational. Okay, so here to prove this, then we say if r is equal to square root 2, then r is an irrational number, right? This is how we say that. Sometimes the statement that we are saying is not in the form of if then, but then you know that, then you must put it in the if then form before proof. Okay, and if for this there are many types. If you have 4, like for x is or for a real number x, and then something, right? And you know that for x, for a real number x, that means if x is a real number, then what happens? So in this case, then we assume, okay, so we let a is equal to r is equal to square root 2, and then b represent the statement r is an irrational number as a is an irrational number, and therefore they'll not b represents r is a rational number, right? When you say r is a rational number, then that means r is expressed in this form. where m and n are positive integers. And then after that, then you prove that. Okay, try this. It's a good exercise. Okay. And then there is okay, from statement, then we have biconditional statement. So biconditional statement, as you can guess, we have it involves two conditions. In this one, this is about the equivalence. This okay. So by statement condition is the equivalence of two statements. Here we use left and right arrow. So we write A, left, right arrow B. And we read A if and only if B, or A is necessary and sufficient for B, right? So the two statements are logically equivalent. When we say logically equivalent, that means A is equivalent to B, right? And this is equivalent to what? A implies B, and B implies A, right? If A happens, then B happens. And if B happens, then A happens. Then from, and again, we know that B implies A is equal to not B implies not A. Sorry, it implies not B implies A is equal to not A implies not B. From this, then you see that if A holds, then B holds. If A doesn't hold, then B doesn't hold. Right? So it shows that the two statements are equivalent. So to prove this, okay, so to prove this, then you have to prove two parts. Okay, you have to prove two parts. You have to prove A implies B, and you have to prove B implies A or not A implies not B. If you can prove the two statements, okay, then we make a conclusion. We conclude that A is equivalent to B, or A if and only if B. Now we come to the last type of mathematical statements, okay, for this topic. It's mathematical statements, and there are many occasions in which we make the statement, okay, in terms of an integer, and this statement is true for example, and this integer is true for many values of n, for the integer n. Right? So we write A in the bracket n. That means the statement A depends on the integer n, right? So A n is true for n is greater, for the integer n is greater than or equal to n naught. Usually it's 1, 2, 3, right? What is this? And then a classic example of this is like when you put a formula. We say summation of n from 1 to k is equal. What is this? Arithmetic series, right? Summation of n from 1 to k is equal to what? Do you remember? Yes? No? It's k over 2 times k plus 1. Am I right? Yes? Oh, this is high school. just a few years. Okay, so we prove this. And you see that this is the, so this formula is true, and this formula is true for what? For K being 1, 2, 3, and so on. Right? This is the kind of the statement we are talking about. Right? To prove that this statement is true, for K being 1, 2, 3, 4, and so on, you see that there are an infinite number of K, right, for which this statement holds. And you cannot, and you see, because there are an infinite number of K for which this statement holds, then you can't prove for each K individually. You can't prove that. You can't prove it, right? Because this is true for any any positive number n. Oh, sorry. Yes, this is true for any positive number K, right? And there are an infinite number of positive numbers of positive integers. So you can't do this. So we use what we call the principle of mathematical induction to prove this. Right? In the principle of mathematical induction, we prove that the first case is true. So we prove that, okay, this an is true for n starting from n naught, right? N naught plus 1, n naught plus 2, and so on. So we need first, in the first step, we have to establish that the statement is true for the first case. And the second step is we establish that if the statement, if AK is true, then A plus 1 is true. So in the second step, you need to prove a conditional statement. So we assume that AK is true, right? And then we try to deduce the okay, and then we must show that A plus 1 is true. Okay. Now to show this, we'll do that on the blackboard. So so in the first step, we have to prove that A is shown that sum of n from 1 to, right? N from 1 to 1 is equal to 1 over 2, 1 plus 1. This is obvious. Usually the first one is obvious. A more difficult will be in the second step, right? So we assume that the summation n from 1 to k sorry, this is k, sorry. This is k. And this is k from 1 to, sorry, this is already, yeah, n from 1 to k is equal to over 2. This is our A standard, right? This is AK. We assume that this is true. Then we show the summation of n 0 to 1, k plus 1 is equal to what? You replace k by k plus 1, right? According to the formula we want to prove. We prove this. We need to prove this. Right? This is what we have to prove. So start from A. Then from A, So from A, from this statement A, then what we have summation n is equal to 1 to k is equal to the k minus 2, k plus 1, right? Then we add k plus 1 on both sides. Okay, then on the left-hand side, what? The left-hand side becomes the left-hand side of the statement we want to prove, right? And this is summation of n from 1 to k plus 1, right? On the left-hand side, then we do them after doing a straightforward algebraic manipulation. Then you will see that on the right-hand side gives k plus 1 over 2 times k plus 2. Right? So that is it. This is what we want. That's it. If you want to find the details on this, if you want something to read, I suggest you find that in the appendix. Okay, in the appendices B and C of Nicholson's book. Okay, we use this book. Some of you may recall this. We use this as our text, right? In second year engineering mathematics.